For the last couple of years, it feels like the entire AI world has been absolutely obsessed with prompt engineering, right? But here's the thing. As we start building more and more complex AI agents, just crafting the perfect prompt, it's not going to cut it anymore. The whole game is shifting from tweaking a single query to a much more rigorous discipline, actually architecting the entire information environment that an AI operates in. So today, we're diving deep into this move to what's called context engineering.
And look, this isn't just hype, seriously. The top folks in the field, we're talking Andre Karpathy, the engineers in Anthropic, they're all saying the same thing. The kind of scrappy art of just, nudging a few words here and there for one response is growing up. It's maturing into a full-blown engineering discipline that you absolutely have to build reliable production-grade AI agents. So what's really the difference here? Well, think about it like this. Prompt engineering is like giving a single, really well-worded instruction. It's a craft, for sure. But context engineering? That's architectural. It's about designing and managing the entire state available to the model over multiple steps. Its memory, the tools it can use, the data it sees. It's a whole different ballgame. It's a true engineering discipline. Okay, so let's get a bit more formal. Context engineering is really all about optimization. It is the set of strategies for curating the absolute best, most high-signal tokens to feed into a model at any given moment. And this is so important because an LLM's context window, it's a finite and, frankly, expensive resource. This scarcity, this limitation, is the central problem that context engineering is built to solve. So why is this such a big deal? Why can't we just, make the context window bigger? Well, it's not a simple bug we can just patch. It's a fundamental constraint baked into the very architecture of today's language models. The core of the issue is straight up mathematical. In the transformer architecture, every single token you put in the context has to be compared to every other token. This creates something called n-squared complexity. What that means is if you double the amount of context, you don't just double the work, you quadruple it. This quadratic scaling is the real villain of the story here. And that brings us to this really useful idea of an attention budget. It's just like our own working memory. An LLM has a finite capacity to process information well, and every single token you add, whether it's crucial information or just noise, it eats away at this budget. It makes it harder and harder for the model to focus on what actually matters. And what happens when you blow past that budget? You get something that engineers are calling context rot. And this is a real, measurable drop in performance. The more stuff you cram into that context window, the less reliably the model can recall any single piece of information from it. For any of you developers out there in the trenches, this is not theoretical. This stuff shows up as painful, real-world bugs. You see the lost in the middle effect, where the model just completely forgets a key instruction you buried in a long prompt. Or in a coding task, it starts hallucinating file structures, suggesting imports for files that don't even exist. And a particularly nasty one is summary drift. This is where you ask an agent to summarize its long history to save tokens, but it actually makes things worse by just inventing details. It's basically writing fan fiction about your code base. Okay, so how do we deal with this? How do we manage this finite attention budget? The key, it turns out, is finding what's being called the Goldilocks Zone, that sweet spot that's, just right. You've got two extremes to avoid. On one side, there's overspecification. This is where you try to hard-code every single possibility into the prompt with complex if-then logic. It just creates a brittle system that shatters the second it sees something unexpected. But on the other side, you have underspecification. This is where you give vague, high-level guidance, kind of assuming the AI just shares your context, which, of course, it doesn't. Both of these paths lead to failure. The Goldilocks zone is all about finding that perfect altitude for your instructions. You have to be specific enough to give the model strong heuristics to really guide its behavior. But you also have to be flexible enough to let the model use its own powerful reasoning abilities to actually solve the problem. And what's really interesting is that this Goldilocks idea doesn't just apply to the density of information in the context. It also applies to timing. Specifically, how often an AI agent should pause what it's doing to actually plan its next move. Yeah, so the research here is pretty clear. The extremes just don't work very well. An agent that plans before every single action, like you see in some of the early React frameworks, it gets bogged down, it's slow, and it overthinks simple steps. But then an agent that never stops to plan is just going to fail miserably at any complex, multi-step task. The best approach is this Goldilocks frequency, where the agent learns to dynamically decide when it's valuable to plan.
This is a really sophisticated metacognitive skill that models are now being specifically trained for using techniques like SFT and reinforcement learning.
All right, so we've got the high-level strategy, but how does this actually translate into code we can write? Let's get practical and look at the production-level techniques that engineers are using right now to actively manage an agent's context. There are basically 4 main techniques in the toolkit. First, you have compaction, which is just summarizing long histories to save space. Then there's RAG, or Retrieval Augmented Generation, which is all about prefetching only the most relevant slice of data. Third is structured note-taking, which gives the agent a kind of external memory or a scratch pad to keep track of things. And finally, you've got sub-agent architectures, where you break down big problems and have specialist agents report back only their key findings. Okay, let's zoom in on RNG for a second, because this has become a cornerstone of modern context engineering. Its effectiveness really lives or dies by one thing: the quality of what you retrieve. And that quality, in turn, is critically dependent on how you break down or chunk your source information. And listen, effective chunking is way more sophisticated than just splitting a document every 500 words. The advanced techniques that people are using involve things like splitting based on semantic meaning to keep related ideas together, or enriching those chunks with metadata like who wrote it or when it was written. This is what makes sure the retrieved info isn't just relevant, but also coherent and contextually complete. It's really the difference between a basic RAG demo and a robust production-grade system. And if you want a direct, practical takeaway you can use tomorrow, here it is. Tons of experiments have shown that for many, many tasks, the sweet spot for chunk size consistently falls somewhere between 512 and 1024 tokens. That range seems to hit the best balance between giving the model enough context to actually understand the information without completely drowning it in noise. So where is all of this going? I mean, these techniques are pretty cool, but they aren't just clever workarounds for today's models. They are the literal foundational building blocks for the next generation of truly autonomous AI agents. The ultimate goal is to get the human out of the loop. We're engineering the systems that will eventually allow agents to manage their own context, to manage their own attention budget completely on their own. They'll learn what information is critical to keep, what can be compressed or summarized, and what's safe to just throw away. And you can see a really clear evolutionary path here. We're starting with the manual and hybrid techniques we use today. The very next step is creating tiered memory systems. Think of it like a computer's super fast RAM for what it's doing right now, and its bigger, slower hard drive for long-term storage. This will let agents swap context in and out as they need it. And this all leads to that final goal: fully autonomous agents that manage their own cognitive resources. And that kind of leaves us with one final, pretty big thought. Once we have successfully engineered agents that can manage their own context, their own memory, their own reasoning, we've basically moved up a whole layer of abstraction. So is the next great engineering challenge no longer about engineering the agent's context, but about engineering its goals? Definitely something to think about.